Uno.
Good afternoon, everybody. It's a pleasure to me to invite to present Professor Rogelio Palomo from Escuela de Ingeniería, University of Seville, Spain. He's going to talk about the CMS experiment, the Compact Muon Solenoid. It's an experiment at CERN. So please.
Okay, thank you. Honored by the invitation by the IFUSP. Thank you for being here. Hello to the people outside online. I will try to explain and motivate the Compact Muon Solenoid, where my group, the group of electronic engineering, belongs as a technical institute since 2017, but we have been collaborating in the R&D collaborations previously for designing the chips, the electronics, part of the electronics for sure, and part of the detectors since 2012. Okay, so we have been collaborating with this endeavor for a long time. I also want to thank to Dr. Frank Harman. Frank Harman is the CMS Upgrade coordinator, and for sure the CMS 2025 induction course, because without the help of Frank, it would be impossible to make this presentation with the photographies, the data, etc. So this is a front view of our detector. That's the Compact Muon Solenoid. Solenoid, why? Solenoid because we have only one solenoid here, superconducting solenoid. Basically, everything is inside the magnetic field, inside the solenoid, superconducting at cold helium, liquid helium temperature, 3.8, 3.9 Tesla. And outside the solenoid, we have only the muon tracker. The muon tracker is important from the engineering point of view because those red iron yokes are the yokes for the return of the magnetic field. Okay, just to contain the magnetic field and not to be dispersed along the cave. Okay. We are at Point-Cinq, the Cessy, in France. Basically, our detector is 100 meters below ground. It's compulsory. First, because the LHC is 100 meters underground, and the other because the muons from the experiments have to be stopped by the ground. So there is a double reason. There, the detector is a 4-pi detector, a name I will say a lot of times in these presentations. A 4-pi means a cylinder geometry with a barrel. That's called the barrel, and you know we have not a lot of imagination. The end caps. Okay, so you see here the yokes in red, the muon system, and the solenoid, and the tracker, calorimeters, the hadronic calorimeters, and the electromagnetic calorimeters inside. By far, this experiment is under control of the US because they are the ones who paid the most. So basically, that's the reason we have a lot of scientists from the US. Brazil is here, Spain is over there, and you can participate in CMS in 2 ways. As a physics institute, so you have access to the data on real time, you can have analysis, physical analysis on real time, and you have to make shifts in the control room over there. Or you can be a member of a non-physics institute, of a technological associate institute, and you are responsible of building the instrumentation and the engineering at that machine. At the end, we are physicists and engineers in both sides, but the only distinction is that the non-authors are non-authors in particle physics papers. Okay, that's only. But we also have our own papers and our own conference, etc. The first question everybody makes about particle physics, because you see the figures, which is hyper expensive and blah, blah, blah. Nobody asks about the cost of a supercarrier, but everybody asks about the money you put here. Okay, so it's a valid question. What is particle physics for? We have been doing particle physics since this man decided to look for radioactivity in the atmosphere. The hypothesis back then was no radioactivity in the atmosphere. The surprise was to find radioactivity and increasing levels of radioactivity in the atmosphere, in a balloon. Reason? Cosmic rays. So the first take-home message is that we are looking to the space, okay? But we are looking to the space into a cave. It's paradoxical, but that's the truth. Not only in a balloon, we are still using balloons, but also in the International Space Station. This is the alpha magnetic spectrometer. It's also a recognized experiment at CERN, so this is also CERN. We are looking for cosmic rays, in particular, a possible excess of positrons coming from outside. So basically, what we are doing is astronomy in disguise. That was the old message 10 years ago. Now it's even simpler. This was February 13, 2023. Under the Mediterranean Sea, near to Sicilia, the ARCA detector detected a monster, a 220 peta-electron volts, coming probably from a blazar. Okay, we are still looking for exactly where that monster came. To make those Cherenkov detectors, I will not go into details here, but basically, to know, in this case, detection needs detectors, detector needs readout, and sometimes the target is for free with permission from the fishes. Okay, it's just a joke. But the point is that to calibrate and to operate this telescope, you need to know about deep inelastic scattering. In general, you need to know about particle physics scatterings, because without scattering, you have no detection. At the end, scattering, any radiation with the exception of gravity interacts with the bulk. Any radiation without gravity, again, electromagnetic, nuclear, weak nuclear force or strong nuclear force interact through surfaces. In the case of electromagnetism, because you have electrons everywhere in the surfaces. In the case of the nuclear forces, because of the short range. So at the end, you need to characterize the detector in terms of a cross-section, okay, in terms of an area. Well, this is a physics case for specifically the 3-kilometer net detector. Okay, basically those are the charge current interactions and the neutral current interaction mediated by Z boson and W boson interacting with a nucleus of hydrogen or with a nucleus of oxygen in water. Okay, so basically that's the origin of your signal. Those particles will go away in a splash at a speed higher than the speed of light in the speed of light in water. So at the end, you have a Cherenkov code. That's the observable. But from the very beginning, if you need to characterize those processes, because those processes are the origin of your signal. So at the end, neutrino astronomy employs scattering cross-sections. Scattering cross-sections are extremely hard to calculate. We do not know to calculate scattering cross-sections beyond a certain level of the perturbative analysis. So from the first principle, from theoretical point of view, it's very hard to go beyond the third loop, technically speaking. Okay. And scattering cross-sections, as you are aware, because it's the bread and butter of nuclear physics, are hard to calculate and harder to measure in fixed target experiments. Why? Because in fixed target experiments, you have tons of background. Typically, you have been aware of colliders because of kinematic reasoning, because in a collider you have a kinematic advantage, and blah, blah, blah. But the real reason from an experimental point of view is that the background in a collider, the background of processes in a collider, is a lot less than in a fixed target experiment. This is crossing symmetry. It's a property of any well-behaved quantum field theory. If this is the process we are interested in, okay, that's a scattering process. An electron goes their business, but interacts with a field, a known field, with some unknown particle. Okay, that's a scattering process. So this is a detection process. If you rotate 90 degrees, you have a production process. That's crossing symmetry. What you learn during this kind of processes is totally applicable to that one. You can see the original reasoning. It's not our original reason from Sean Carroll, from Caltech, but it is very well explained in that paper. Okay, so another take-home message, you will have a lot during this presentation. Multi-messenger astronomy is possible thanks to Collider. Think about the next time someone asks to you, which is particle physics for? It's for looking at the galaxies, for looking at the universe in general, okay? What do we measure in a collider? This is a cartoon of a collider just for you to get used to. This will be the tracker. Those are the calorimeters. You are looking at a Kaon meson production. We produce their strange quarks, part of a quarks atronized in a jet. The Kaon decays into a couple of P plus, P minus. So we track the path of the pions and also the total energy deposited in the calorimeters. What are the things you measure in this kind of instruments? The first one is luminosity. Which is luminosity? It's a measure of the amount of particle collisions you will have in the experiment. The second thing is, you need to know is identification of particle by track pattern recognition. So this is the first observable. Without this integrated luminosity, you don't have cross sections. Okay? So this will be detected by the trackers and the calorimeters. The luminosity or the integrated luminosity will come from luminometers. Once you know the luminosity, your next business is a combination of a mass spectrometer with a very strong magnetic field and calorimeters. The name calorimeter is because the whole remnant kinetic energy from the particle is deposited there and totally absorbed. I will elaborate further. At the end, you use relativistic kinematics because the thing to consider or the thing to measure is the invariant mass, for example, the invariant mass of the Kaon and the decay time of the Kaon. Okay? And you have to use relativistic kinematics, in particular in the tracker, because those things are flying out at the speed of light, basically. And there you can see a real analysis in that cartoon. Okay, so this is what we work for. Production cross sections. There you have the production cross sections known up to April this year. With those data, you are free to construct new observatories for the universe, because this is what you will need in your first calculation in the detector you put in your telescope. Telescope nowadays is not a Galilean telescope, okay? But at the end, it's a telescope, because any telescope is used to know about a radiation and pinpointing the origin of that radiation. That's the basic definition of a telescope. Journalists are eager for discoveries, okay? We are not interested in discoveries. Discoveries is just to make money or to collect the money, to gather the money. But what we are really interested is in production cross sections. This is a detail of our experiment, CMS, a solenoid general purpose 4P detector. Basically, this is the beam pipe, another beam pipe here. That's the collision point. This is steel. At the collision point, we use beryllium, solder. Well, there is only one company in the world capable of soldering beryllium and steel. Beryllium in the center, because beryllium is the lightest metal known to man. Okay? And we need beryllium because it's the most transparent, maintaining the high vacuum we have there. It's a technical point. If you are a mechanical engineer, it's a thing. Okay? Then you have yokes, you have the silicon trackers in several flavors. You have the crystal electromagnetic calorimeter, I will detail in a moment, and the hadron calorimeter. Basically, this is an amount to compare the size. 40,000 tons. Okay. This is the end of the data taking. This is made in server farms, part at CERN, part distributed in the whole world through the grid. So basically, we have one big mainframe scattered around the world. Okay? So at the end, this is what you are looking for, and from there you compare your calculations, phenomenology, your calculation of cross sections and the prediction of your processes to these kind of things. In particular, this we typically tag our experiments, our splash images in that way. Okay. We are 6 months of the next stop. Why the next stop? This has been our history. We detected the Higgs in round 1. It was unexpected, but the machine worked perfectly, the whole machine, the LHC and all the system and CMS. We were the ones who detected the Higgs. Okay? We knew about a possible event in Higgs around November 2011, and we found, Guido Tonelli found the people from Atlas said to them, look in particular in the gamma and in the 4 leptons channel, because there we are looking at a 2.2 sigma excess of events. Okay, that was the message, and in July, the 4th of July 2012, the world was aware of the Higgs boson. So we are more or less here. During 2026, in the summer, we will stop the LHC, and here in CMS, this is the Bâtiment 40, the building number 40. That's an image of CMS compared with the size of our analysts live here, and the Atlas people live there. This is the hotel at CERN. Okay, so during this long shutdown, we will make a total refurbishment of CMS. In fact, it will be a totally new detector. We will only preserve the magnet, the yokes, and several parts of the external muon system. The rest of the detectors will be totally brand new. So, if you are interested in making instrumentation, that's your epoch. Okay, that's your time. If you are interested in making particle physics, take into account that there will be not another collider in the world up to, guessing, 2045. At 2045, I will have grandchildren, I hope. At 2045, everybody here will be senior. So again, it's the good time to start instrumentation now. Which is the physics case? The physics case is described in this document presented to the LHC committee. That's the committee to decide the new investments. It's a document from 2015. Okay? In 2015, the technologies for the new CMS were still under development. We were not sure that we could withstand the requirements or fulfill the requirements, but the physics case was extremely clear. During the run number 1, essentially in the Z4 lepton channel and also in the gamma channels, we detected an event, a series of events compatible with a Higgs. Okay? And we were very cautious about compatible with Higgs. We still say compatible with Higgs. At CERN, we don't say we have discovered the Higgs. LHC can be described as a top quark factory because this is a gluon from one proton, that's a gluon from another proton. They interchange a top quark. Top quark is the quark that has the biggest coupling to the Higgs, so it's natural to produce with an hadron collider, with a proton-proton collider. It's natural to produce Higgses this way. Okay, and the channels, this is the Z4 lepton channel, is from the decay of the Higgs. In the cartoon, you look at the count, the 0 count decay. So basically, it's the same history, but with another particle. And this is the discovery at run number 1. That's the number of events in beams of 3 giga-electron-volts. So basically here, you are between 89.5 to 91.5 giga-electron-volt of resolution. This is a Z boson, or the signal, compatible with invariant mass of a Z boson. And this is the signal, the number of events compatible with the mass of a Higgs boson. For the future, this is a CMS simulations that typically we run everywhere. For example, here in Sao Paulo, in the UNESP, in the analysis group of UNESP, where they run a lot of Monte Carlo analysis predicting the possible invariant mass of a Higgs interaction, okay? Because we know nothing, we know that the Higgs particle exists. We are not interested in the Higgs particle, I have to say. It has no interest at all, with the exception of one thing. The Higgs boson is the only free boson from the Higgs field. From everyday life, we're interested in Higgs field. Thanks to the Higgs field, the weak force has very short range. Okay, and it's very, very important because if the weak force is not absorbed by external Higgs field, we will be living in a supernova way. So it's very important because the coupling of Higgs to the Higgs field with the weak boson is responsible of limiting the monster of the nuclear weak force. In the high luminosity LHC, our intention is to have a Higgs factory producing millions of Higgs boson during the lifetime of the experiment and 125,000 pair of events like this. To know between the self-interactions of that field. Is that field stable enough? Can be unstable for some reason? It's very important because at the end, the Higgs field is the responsible of maintaining this world stable. And who knows? Probably new physics at which scale, long cross-section, who knows? For the moment, I can say that supersymmetry is not favored. Dark matter, who knows? Extra dimensions, probably not. Long life particles, we are designing new experiments outside CMS along the pipe just to detect long life particles. But when you are searching, you cannot say no from the very beginning. So stop about the physics case. It's all about high statistics and better detectors. There you can see, you can have more details, a lot of details about. Now from the point of view of kinematics. This is the nominal luminosity, instantaneous luminosity of the LHC. It was in 2000. This is a splash from 2016. Basically, is the same today. And this is a typical event, reconstructed event in 2016. This will be the future. So the point is that the instantaneous luminosity will be one order of magnitude. It's not a big thing, but remember, from the luminosity equation, the interesting observable is not instantaneous luminosity. That is proportional to the rate of events. We are interested in events. But one thing we learn from the LHC every day is about the reliability of the machine and the reliability of the detectors. So we can now, we know for safe today that we can run the machine during 1 year, 2 years, 3 years, etc. It was not clear at all at the beginning of the LHC experiment. Remember, we inaugurated the beams in the 8th of September, at the end of September 2008, and the pipe exploded 10 days later. Okay, so the important thing is not on, it's important, okay, the instantaneous luminosity, but the thing is the integrated luminosity. So we will have 200 of events, pileups, simultaneous events, and this thing, to have you in the mind, this is not a single event. You have to consider that we have an event like this every 25 nanoseconds. So the best way to imagine the activity of LHC is like a sustained nuclear explosion. Okay, the flashes are coming in our temporal scale basically instantaneously. Okay, the machine is the LHC, the magnet, I will not speak about the magnet. The trigger DEQ computing is always updated. I will say some words about the trigger, but I'm interested today in taking the message of instrumentation because at the moment we are finishing the data taking and we will start the refurbishing of the whole systems. Tracking, because the tracking will become a timing tracker. Up to now it's only a space tracker. Okay, we can track along the along the space, but not along time. The calorimeter is becoming a tracker. We invented the particle flow in the tracking during analysis at CMS. Now everybody does particle flow. With a tracker calorimetry, the particle flow, in particular the hadron particle flow, will increase the precision of our measurement. So it's a big step. And the muon system, that is also a tracker. After that, you go to the physics and go around, refining your knowledge. Okay, from the detector channels, this is the front-end electronics. Detectors, a lot of flavors of electronic or of channels. The front-end electronics will have the detector here, amplifier, filter, shaper, basically the signal conditioning. Then you will have a digital process, buffer, extraction of features, because at the end you are making the first analysis, another buffer, formal and readout, etc. The most part of the data goes to storage, okay? Because even if you have not fresh data, you will be interested in having the whole data set for ulterior analysis. The trigger is experimenting a small revolution, not so small because it's made with FPGAs from Sevilha Institute, but the leadership is from Imperial College. And we were the first in using artificial intelligence, AI, artificial intelligence, inside, in particular, autoencoders. Okay, so the trigger has the capability for, up to a point, to self-learn about processes and to refine the learning in the FPGA, in the weights of the neural networks in the FPGA. So basically, in the phase 2, the level 1 trigger will capture data from the muon system and the calorimeters, plus from the outer trigger. This is extremely important because the particle flow will be made now also in the outer tracker. The main mission of the trigger is to make a first selection for a data rate of 400 millions by seconds of data flow to 100, 700 kilohertz. We have another trigger, the level 2 trigger, but this is a conventional, not so conventional, but it's a server farm in the Poinsang and Cessy. And from there, we have distributing the data from along the grid, first to the computer data center in Meran, and then to the rest of the world. Okay, this will be, hope it will be, a level 1 trigger reconstruction someday in 2030. So the granularity coming from the high granularity calorimeter is, you can make a zoom. So you are looking at identification of hadrons generated during the hadronization process from the vertex. Also, you will have information from the outer tracker, okay? So you can follow not only the calorimetry, but also the momentum of the particles from the vertex. It will be very easy. And for sure, we will be more confident that our trigger is not deleting without permission important data. Compare with the actual trigger, okay? In the actual trigger, we only look at the electromagnetic calorimeter and the hadron calorimeter. So the increase of resolution and the possibility to avoid errors, mistakes made by a bad programming, not a bad programming, but not a very well physics-oriented programming in the trigger will be avoided, or unless we try to. Okay, let's begin the analysis of the detector from in order of importance. The most important, by sure, is the Brill. The Brill is the system responsible of giving to us luminometry data. This thing. This is the even data rate. This is the visible cross-section. It's very well related to the production cross-section. Okay? Those are the parameters you need to look to determine the luminosity. And today, the main luminometer is the hadron forward calorimeter. So basically, we are looking at kinematics data from the beams, because in any particle physics, you need data from the collision, the splashes, okay? And you also need data, kinematic data from the beam. And you combine both in the cross-section, in the production cross-section. There you can elaborate more about its 2020, LHCP 2020, so it's very modern. Another view, 3D view, just to remark that luminosity measurement absolutely essentials, and you have several. This will be the luminometer in the phase 2, okay, in the brill, beam radiation, instrumentation, and luminosity. This is the first batch of sensors you need. You will not discover nothing with the brill, but without the brill, it's impossible to discover something. Okay. This is a cross-section of CMS. That's the interaction point. So the first thing you have is the silicon tracker. Remember, this is the magnet. So the tracks will be curved along the magnetic field because you are looking at a charged particle. Here you have a muon. There you have an hadron. There you have a lepton, or a lepton, a charged lepton. And those are particles that they have basically no charge. Those are neutral hadrons, mesons in particular, and this is a photon. Okay? So basically, looking at the track without taking any further measurement, just reconstructing the trajectories, you can identify particles. That's the second thing you need. Remember, luminosity is the first thing, identification is the second thing. After that, you go into relativistic kinematics to determine mass, decay, and momentum, in that order. The cross sections in the whole system. In particular, the muon system is a sampling tracker. Why a sampling tracker? Because the penetration power or the stopping power of the muon is very limited. So we need to increase the amount of stopping material to avoid the muons escaping outside of the detector. Okay, how trackers work? There are several technologies for trackers. For example, Alice employs a time projection chamber gas tracker. But from the very beginning, we decided to use silicon trackers. Which is a silicon tracker? A silicon tracker is basically a lot of tiles in concentric rings around the collision points. Every tile here is full of the silicon detectors, the electronics, the readout electronics, and the data sending and data inputting commands. Okay, so basically you are looking at square meters of electronics surrounding the barrel and around the end caps. At the end, so you make several measurements and you make those beautiful reconstructions, etc. We have two trackers, the outer muon system out of the coil and the inner tracking system. The inner tracking system is subdivided in the inner or pixel tracking and the outer or strip tracker. In the new phase grade, the outer will be also a pixel tracker partially. Okay, so this distinction between pixels inner and strips out will be not true. Will be only a secondary distinction between the size of the pixels. But we will pixelate everything. So we will take in snapshots of the things happening there. It's important for seeding and vertexing to know exactly where this splash starts and from where it starts. If it is from a primary vertex, from the collision, or from a secondary particles that decay, for example, a big quark, a boson quark, or etc., before making hadronization or making a meson. Muon tracker. This is our gas system. Essentially, they are ionization chambers in couples. The increase of resolution will be around 1 nanosecond of time resolution, almost halving the dead time. Actually, it's around 2 nanoseconds, and will be thanks to the front-end electronics using ASICs developed basically to this thing, and FPGA. So it's important that the electronics there, it's almost discrete electronic, almost, but it's extremely important to increase the time resolution. And also, we will add new detectors in the very forward, here and there, using segmented pixel gas detectors, the GIMS. For some reason, the GIMS is not there. Anyway, because I was expecting for the GIMS slide. Anyway, how works a calorimeter? We have two kinds of calorimeters. We have an homogeneous one. The homogeneous is the electromagnetic calorimeter, and a sampling calorimeter. Both are advantages and disadvantages. The real reason we use a segmented or sampling hadron calorimeter is because it's too expensive to have a full homogeneous hadron calorimeter. But the sampling calorimeter has a limited energy resolution, but it can give to you a detailed shower shape of, in terms of longitudinal segmentation. You can make measurements of these lateral splashes. Here you see nothing because basically you are absorbing the whole energy into the calorimeter. Okay, but both are good for the hadrons, for the leptons and for the gammas. We prefer this one, and that was the reason, in particular in the gamma Higgs channel, the reason we were the first to look at signals compatible with the Higgs. And for sure, using our muon system, we were also the first to look at the ZZ for lepton channel. This is the electromagnetic calorimeter. We use crystal extremely dense, tungsten and lead oxides with new chips. This is the layout. Basically, we use the CATIA and the light DTU. The crystals will be reused, but we will use new silicon photomultipliers here because the signal to detect here is that's a scintillator, an inorganic scintillator. So basically, the signal to see here is a blue light. In particular, it will add precision time also. This will be one of the first precision timing calorimeters. We also have the hadronic calorimeter. Is segmented. We'll still have some plastic scintillator tiles. This is an organic scintillator. That's just for you to know what is the pseudo rapidity. Pseudo rapidity is a strange way in experimental particle physics to speak about angles. Okay, that's all. So we will have the barrel, the end cap, the outer, and the forward. But we will make refurbishment of several parts of those calorimeters to increase the precision and also the timing. In particular, we will use again silicon photomultiplier, and we'll route to new readout electronics. Okay. For particle flow in the hadronic sector, this is brand new. It's the high granularity calorimeter. It's in the end caps. It's here. We will reuse part of the plastic scintillators, but now we will have silicon sensors like this in hexagonal silicon modules. Every module have a HC CROC in 130 nanometer scale, new readout chip from the Omega Lab in Paris. Look at the amount of radiation damage. Silicon detectors can withstand with this huge amount of neutron equivalent damage. Silicon photomultipliers basically die at 1 order of magnitude less. Okay, that's the new tracker. In particular, this is the outer tracker. In the outer tracker, there will be a new, the actual outer tracker gives points, okay, points at every tile. The new outer tracker will combine using the same electronics between two sensors. The sensors in the outer tracker are the two strips or the macro pixel strip, here, and there. Okay, so to discard particles with extremely high curvature. Those are low transverse momentum particles that we are not interested in looking at because basically those particles come from the interaction of the splash with the elements in the detector. So basically, this is noise. So having this thing, we have to totally renew the outer tracker. And also we have the inner tracker here. Look at the size. This is 1,200 millimeters. So it's that size, okay? And you have to put the whole system, refrigerations, data taking, etc., in that barrel. There is not a lot of room there. And this is for the pixel, where you have the less room is devoted to the most sensitive and the most precise system, the micropixel. There, the total ionization dose is around 1 gigarad for 2 years of operation, 5 years of operation. Okay, so we have to design, taking into account that the TD in those readout chip is extremely huge. I was working in the RD53 collaboration in that chip. Okay, just a detail of the new readout chips. If you know nothing about microelectronics, then you have nothing to do with the tracker. Sorry, but it is not a big deal. For example, the MPA2A6 is designed by a few of people. The SSA2A6, again, designed by few people, because they are designs extremely repetitive. But if you are not a microelectronic designer, sure, you could be a tester, because you have to test this thing in real conditions, in the lab, during the installation, during the calibration phase. So if you know nothing about electronics, don't worry about it. You will learn at CMS. And this is a detail of the macro pixel strip module in the outer tracker. Okay, we developed 1, 2, 3 readout ASICs specifically for increasing the capabilities of the outer tracker to respond in 40 megahertz and to have timing capability. The amount of single event upset here is not huge, okay, because they are not in the inner tracker. It's the most savage volume is in the inner tracker. In the inner tracker, we designed a new chip. It was an effort that took 10 years. This is Sevilla, okay? So several institutes and university, all of them microelectronic designers, FPGA designers, etc. Why so many people to make a chip? Because this chip has to withstand a huge amount of radiation, 1 gigarad in 5 years, and also a huge amount of single event upsets. We have doing our best to reduce the single event upset to a manageable rate, 100 Hz. So we will have every second we will have 100 single event upset, and I have to recover these electronics. These electronics here. Okay. The space is so limited that you cannot have DC-DC converters. The cabling cannot go through that structures because cable is made of copper. Copper is a high set atom, and you don't want to see the copper in your analysis. So forget about copper, thick copper. Forget about DC-DC powering, and we had to develop a new powering scheme. It was a total nightmare during these years, yeah, because it's difficult to stabilize. Now it's stable. It's a serial powering. So there are a lot of innovations in this very small thing. It's that size. Okay, you can see the size. This is a clock number 2. Power consumption is another thing, because if your power consumption is huge, it will be impossible for the refrigeration system to maintain the minus 15 degrees Celsius in the structure. So it was a challenge for 10 years. Our final paper, 70 pages, has the full bell and whistles of our effort in those 10 years. Okay. Those are the details of the chip. It's up to you. And this is a description of the chip. Sevilla was working here, because I was working in the power on reset. Also, we were working in the clocking scheme, and also we were responsible of the single event upset simulations at several levels, just to have no single event upsets. Okay, and basically we have noise levels, ridiculous noise levels, and we make a lot of digital analysis here before giving those data to the trigger. To the trigger, no, to the data system, because this is not coming for the trigger. Okay. The first thing you have to consider in any readout chip is the pixel array. This is a 4 pixel, 1 pixel, an analog island surrounded by digital wiring and digital elements in very regular structure. And we have a sensor leakage compensation, a Grumman-Agger scheme, a charge-sensitive amplifier, then the discriminator, and we can program the discriminator to different thresholds, just with 2 levels of detail, and also to distinguish if that is a real signal or if it is noise or a glitch or whatever. And for radiation hardening against the total ionization dose, we use the techniques of hardening by design. In particular, in the analog part was not very difficult, because in the analog part you can use big transistors. In the digital part was a problem, because the standard cells typically are very tiny. In particular, the string 0, the minimum standard cell, digital standard cell, was discarded. And in some places we have to design our standard cells. Okay, it's not typical when you are a digital designer. Typically, you take standard cell IP blocks from the foundry. But in this particular case, in some places, we have to design our own digital. So it was an effort. It's just to explain why we are so slow developing a single chip. Okay? Several schemes for withstanding or reducing the single even offset rate in the pixels, because there is no more room in the pixel. Here, we use voters. In the global configuration and state machines, there in the digital chip bottom, we use not only voting with feedback, but also we skew the clock. We use 3 clock with an skew to avoid glitches, to avoid single event transients. Even with that effort, our CU rate is 100 Hertz. Okay, a new guy in the block. We will put new minimum ionizing particle timing detector layers in the barrel and in the end caps. This is what timing will gives to us. That's the longitudinal view. If you can separate in time those events, then you have 2 events. If not, you have a pileup. So you don't know if this is coming from a real process or it's an entanglement of process you know nothing about. In the case of the actual LHC, the pileup is a problem that we can live with. Okay? For the high luminosity, it's impossible to live with the pileup expected. So we decided to develop brand new technology to distinguish this is a typical pileup. Okay? So something that is ambiguous in 3-dimensional space is unfolded in a 4-dimensional space. Very important. And using brand new technology in the barrel and brand new technology in the end caps. This is the technology that we use in the barrel. Those are scintillator tiles of LISO doped with cerium. It's in the mood, I don't know. It's a very brand new scintillator used in a lot of laboratories today. And we read the scintillator light with silicon photomultipliers. But the silicon photomultiplied, the gain of a silicon photomultiplier is destroyed beyond a fluence of 10 to the 14 neutron equivalent, 1 MeV neutron equivalent by square centimeter. So in the end caps, where the amount of radiation damage is 1 order of magnitude bigger, we cannot use LISO. We cannot use silicon photomultipliers. LISO is perfect, okay, because it is a dielectric. And we will use low gain avalanche diodes. A totally brand new detector that is able to increase the amount of signal, because the electrons coming from here, okay, will get an avalanche to increase the amount of electrons and to get more signal. It's very important to get big signal, because those detectors will have only 50 micrometers thickness. Why so Why that thickness? Because the drift time is important. Remember, this is for a timing, okay? We need 30 picoseconds of resolution in time. So the amount of time we need to collect the electrons and to clean the detector has to be reduced. The best way to make that is to make a thin detector. But you cannot thin the detector everywhere you want, because remember, a capacitor, this is when it's reverse biased, is basically a capacitor. If you reduce the thickness, you increase the capacitance. If you increase the capacitance, the slew rate, the speed of the response of the detector is reduced, because basically your signal, the speed of your signal, that's voltage, is reduced by the amount of capacitance. You have to make a deal, and for that deal, we were in the RD50 collaboration during 10 years. RD50 collaboration was a 20-year-old collaboration, ended in 2023. Now it's called DRD3, okay? And we were the ones who decided to change the bulk of the conventional path pin detectors, or the pin detectors, instead of P in N, N in P. We also decided to change the way of making the crystals of those detectors. Instead of the conventional Krochalski method that we use in electronics, we use a floating zone, another process, okay, controlling the amount of oxygen we put in. For what? For capturing in the device the vacancies and the defects, basically to avoid the diffusion of vacancies and defects along the crystals. We also invented the three-dimensional detectors. Okay, in the case of a three-dimensional detectors, we change the biasing path and the drift path. Now they are different. I will elaborate in a moment. And also we invented the LGADs. Okay, so basically we invented all the detectors we are putting, with the exception of the gas, in RD50. This is a low-gain avalanche detector. It was first developed in Spain, Barcelona, by the group led by Salvador Hidalgo. Salvador is one of my scientist fathers back in 2013. I was collaborating with them in the simulation of this thing. This is one of my TCAD simulations, okay? After developing this, 300 micrometers, we thinned the device up to 50 micrometers. This is only for mechanical purposes, and there is no TID effect in this buried oxide, because we using reactive etch technique, plasma rear, we put contacts, metal contacts. So basically, the charge is accumulated there, but has no effect. Okay? In this device, electrons take more or less 3 nanoseconds, holes 5 nanoseconds in 300 micrometers. You have to divide by a factor of 6. So this is the perfect timing detector using silicon. And after a lot of simulations, this was a RD50 workshop basically devoted to this problem. Okay, sometime I remember I was in Krakow, because we discussed a lot of sizes, simulations, etc., to get the perfect deal between reducing drift time and not increasing the capacitance to reduce the slew angle, or to increase the slew angle. Okay. A detail of a path silicon LGAD. Just for you to have a comparison, we have a gain of 20, 10, 20. An APD has a gain of 100, in the 100s. But this increase of gain means more noise. And we only need the gain to compensate that the amount of charge we collect in the device is reduced by a factor of 6. So with a small amount of gain, we don't introduce a lot of noise. Again, it's a balance in the design. It took several years, and we are still working in that, because those are different. Those are simulations that I made years ago using lasers, simulated laser with the gain, things that you are doing right now, for example. Okay, and also we started to dope this thing with carbon spray, because carbon spray is another technique to avoid the diffusion of vacancies and defects. In the lab, in particular in the CNM, not in the Bruno Kressler, in the FBK, in the lab we can withstand even a little more than 5 to the 15 neutron equivalent 1 MeV by square centimeters. Okay, but nowadays LFoundry is trying to reproduce an industrial scale. The process, Micron in the UK is also trying to reproduce the process at an industrial scale, and Hamamatsu is trying to reproduce the best LGAD today, because that was an email a week and a half ago. The best LGAD nowadays is coming from Hamamatsu and can withstand a level of 1 to the 15 neutron equivalent 1 MeV by square centimeter. Okay? But this is about scaling the process, not making small batches of detectors. It's for manufacturing detectors in the thousands. Okay? But they will, for sure, dominate the process of carbon spray. And that's all. So if you want to work with us, send an email. Questions?
Well, thank you for your colloquium. And now the colloquium is open for questions. Yes, please.
Thank you, Professor, for the very nice talk. I have a quite naive and broad question. As you said, we are 6 months from the Long Shutdown.
Yeah.
And I would like to know at what point of the upgrade we are right now. I mean, we are still developing things, or the Long Shutdown will be just for installation, calibration, testing?
The timing layer is almost totally developed. Now we are building the timing layers in different production labs in Europe. Okay? The Endcap timing layer is still under development, because the scaling of the LGADs at the industrial scale and long production runs still has some problems. We have time, because this will be installed probably in 2 years and a half time. And probably there will be no problem. The Croc V2 is now working perfectly, and they are starting to install. There is no problem in the outer tracker. And the Hadron High Granularity Calorimeter is basically finished, because it was the first to start in 2016, in between 2016 and 2018. Take into account that you are the producer, okay? The institute producing things, or the factory producing things. We, as customers in CMS, basically we believe nothing coming from you. So we will make our own tests. That testing phase started in 2015, coincidental with the document presented to the LHC for the phase 2 upgrade, and it started with the calorimeters. So, with the exception of the LGAD, because it's a brand new technology, it's totally imprescindible, but you need that technology, but it's a technology still not in production phase. Everything is basically done. Okay. More questions, please. I'm here to answer your questions. Sorry.
Thank you for the colloquium. I have a question that, are you able to measure all the energy which comes from all the particles after the reaction? And you are able to compare this with the initial energy of the particles that will produce this region?
You have
and is it possible that you are missing something, for example, dark matter particles? What's the precision of your measurement?
We hope not.
Do you hope it's not enough?
We hope not. No, it's a very important question. It's related to analysis, not to technology. The analysis people, with their huge computer and their wonderful brains are responsible of making a lot of Monte Carlo analysis to predict this plot. In particular, this is a predicted plot. Okay? Those points are the points from the data taking. So, is our trigger losing some information? Today, I have to say yes, sure. But take into account that we are not looking for everything. When you design a detector that size, you need to know which is your main objective. Our main objective was the Higgs. After the Higgs, our next objective was to increase our knowledge of the weak interaction. In particular, the vector, I think, named as vector boson fusion. We published the vector boson fusion weeks ago or months ago. Okay, and the other thing you look for is for strong force measurements. Basically, we discovered, I don't know if it is important for the future, but basically we detected a tetraquark and hints of a pentaquark. But we cannot look for anything. Okay, it's important to know that you have to tune your detector to look at particular channels. Even from the very beginning, as I said in the blackboard or in the green board, okay, we designed specifically CMS to detect the gamma-gamma channels and the subset for electron channels. Specifically from the very beginning. That's the reason our name is Compact Muon Solenoid. The unexpected was to discover the Higgs right at the beginning. Okay, there is a very interesting cross-section plot in every CMS office, because we basically discovered the whole particle physics up to 2010 in the pre-run number 1. So we know for sure that the process known up to the particle process known up to 2010 were rediscovered by CMS, just for calibration. First thing. Second one, are we losing information about the Higgs? For sure. That's the main reason to have a high luminosity. And also take into account that with an hadron collider, a proton-proton collider, to look for strong force process, quark events, is extremely difficult because the amount of strong force background noise is huge. Okay, to increase the precision of a Higgs measurement, taking out the background noise from strong force needs another machine, needs a lepton collider. But a lepton collider, and I will, because your question is extremely interesting. A lepton collider has a problem. Before the Large Hadron Collider, we had the Large Electron Positron Collider. But the electron and the positron are very low mass. I don't know if the neutrino has mass, okay? Probably. But up to now is the lowest mass particle with mass. And when you make a particle with mass come into a ring, you lose a lot of energy because of Bremsstrahlung. In particular, we have to close the LEP phase 2, because probably we detected the Higgs in the LEP phase 2, but no statistics enough to declare an experiment. Also, probably Fermilab detected also Higgs events, who knows? But we have to close because basically we were adding energy with the accelerators, and we were losing that energy in the ring. For that reason, we went into a proton-proton collider, because the proton has, as you are aware, 2,000 times more mass, and the Bremsstrahlung is negligible in this facility. If you want to go to an electron collider for this in the tera electron volt range, you need a tunnel of 100 kilometers or even more of perimeter. If you have the money, we will make one. But it's a huge problem of money. The LHC was taking advantage that the tunnel was paid for 20 years before. So at the end, you have to stand between the interest in physics and the amount of money you can gather from the people. Okay? Thanks. More questions? Joao?
Another one?
It's a colloquium, so feel free to make opinions or whatever, because this is not a palestra, it's a colloquium.
So how you discriminate the pulse in the scintillator styles? The plastic.
Again, sorry?
How you discriminate the pulse in the different scintillator styles?
The boost?
The pulse. Pulse.
The pulses?
Yeah.
In the scintillator?
Yeah.
Well,
By time?
basically, no. In the plastic scintillator tiles, we have no timing. So basically, we detect a flash, and that's all. In the case of the new silicon in the high granularity, we also detect the timing. But in a plastic, it's difficult to locate timing there, because it is a plastic, basically. Okay? The way you produce the signal in a scintillator is not as precise as the way you produce the signal in a solid state ionization chamber, in a diode. That's the reason. The other name of CMS is the completely made in silicon detector, as we were joking 1 hour before. Another question?
Hi, thanks for the very nice presentation. So, a two-part question. The first one is, you showed that the optimal vision for the L1 trigger if all the other tracker information. Will it also ideally have information from the timing layers? The L1 tracker for the high lumi?
In the trigger, no.
No.
In the trigger, no. No, because at the end, the amount of data you can process in real time is limited, even with today's technology. So to add the tracker is a big step. The timing is considered in the L2 trigger, in the Vincent Cessy, the bâtiment, in the building. Okay, sorry, but sometimes I speak in French. Okay, but the short answer is no. Timing is not for the triggering. Timing is for the analysis, because who knows? Who knows? At the end, it's a thing, not so simple, of routing cables, fiber optic cables, to the trigger. And the trigger is updated at every moment. There is no a phase 1, phase 2 triggering update. It's triggered it's updated at any moment. So if we have new FPGAs, even faster FPGA, it could be. But at the moment, the short answer is no. Second question?
So as you mentioned, the trigger also have to take into account what exactly you are trying to focus on your machine on in terms of signals, what you're trying to analyze. Now there's this kind of pushing of the community to look for these long-lived signatures, which are very challenging to trigger on. Is there any thought put into the electronics and detector design team for high lumi that is trying to take into consideration these long-lived signatures for both the triggering and the tracking system?
No, the trigger is hierarchical. Okay, so once the level 1 trigger decides that that event is not interesting, you lose that event. First thing. We always are in fear of losing data, but we are limited by reality. So at the end, but if you lose, if the trigger decides that that event is not interesting, you throw away the event. It's not a big deal, okay? Around 90x%, 98%, correct me if you know the exact names, the exact figures. About 98% of the events in the LHC is pion production. In fact, we use pion production to calibrate the detectors. But pion physics is very well known, so it is not for discoveries or whatever. It was measured in Fermilab and in other colliders, even in the lab. 2% is count decay. There are some open problems in count physics, but we have specifically devoted experiments, in particular the NA62, dedicated to count decay, to the asymmetry of count decay in terms of matter antimatter in the SPS in the North Hall experiment. So again, counts is not so well known, but almost well known physics. And 0.1%, 0.2% is new physics. or not new physics. The Higgs is known since 2012, but physics outside of the typical physics produced in a proton-proton collider, kaons and pions. So if you are losing data, okay, you have to live with. But at the end, it's not a big deal. You are losing 0.00x% of the data because you need to reduce the amount of data. For us, it could be wonderful if we could take advantage of the full 40 megahertz data taking in real time. But nowadays, with processing electronics, it's impossible. Okay?
Well, thank you.
Any other question?
Nice talk. I'm concerned about the damaging the detectors. How do you deal with that? I mean, detectors in electronics. You have to check that
Yeah.
often. What's the frequency for checking that, or you don't check?
The first thing is please come with us to the DRD3 collaboration, okay? Because it is a totally open problem. The first thing to consider here is that we are renewing the inner tracker almost every 2 years, 3 years. So this thing will not last. So we are running against time. We have increased the radiation damage by 1.5 order of magnitude, okay, from the previous generation, using techniques as NMP, using techniques as three-dimensional detectors, things like that. Probably I will show you three-dimensional because I guess they were in some slide. No, because I decided to take out, too long. But sure, our detectors are hardened, but the amount of radiation is also increasing. So it's always, at the end, the number of years you will have the inner tracker properly working is exactly the same, 2 years. Even considering that we are not working at room temperature at the moment, at minus 15 or minus 20 degrees with a CO2 cooling system. Okay.
So it's kind of a number question.
There are no numbers.
The question is, where exactly do you put the LGADs and how much LGADs in the system?
You put the LGADs here, okay, with a number of channel of 4,000. So the number of LGADs is 4,000 for every Endcap.
Where is this? Sorry.
This is the barrel. This is the. It's this is between the. Basically, it's here. Okay. This is the electromagnetic calorimeter. That's the hadron calorimeter. There is a small space in between. There you put in the barrel, that one, and in the end caps is exactly the same position.
Okay. Thank you.
Okay. Yeah.
It's more for discussion, I think, because we're discussing right now. So we talked about what we would be interested on studying more on regarding physics and the future of particle physics and etc. and colliders. So I was wondering if you could talk a little bit about it and the possibilities and about the physics that we are interested, and given what we have, what could be interested for us to use this knowledge for the future in the sense of the new proposals, let's say, for colliders.
Sure. In fact, we were discussing yesterday about. First thing, in Europe, we have almost lost the microelectronics industry. Okay. Nowadays, the microelectronic industry is supported not by CERN, but it is supported by the automotive industry. In the very beginning, 30 years ago, CERN decided to join the IMEC collaboration, and the IMEC collaboration is giving to us, the university, the possibility of developing at reduced prices, developing microcircuits. So indirectly, not so indirectly, okay, CERN is also responsible of supporting the capability, the designing capability of the European people, for example, like me. To have numbers in mind, one batch of RD53, it's around of chips for testing. I'm speaking about 200 chips or whatever. It's 300,000 euros, because that's the real cost of a chip, okay? Even with the size of CERN, we consume chips in the thousands, more or less. It's not a big number. To get investment returns and gains, economical gains, in the microelectronic industry, you need productions in the order of tens of millions. Without that, it's impossible to balance your sheets. But in Europe, we have a market. And to have chips, you need designers. You need people working on. People from the RD53, friends of mine, they were working in RD53. Some of them are now professors in the university, but other people is now working in the renascent electronic industry in Europe. So if we can compete with the Taiwanese, one of the make it possible is the CERN effort. So I think it's important. Even if we discover nothing, just the return in terms of maintaining the human brain capability in a territory that the CERN is doing is critical. If not, everybody will be speaking Cantonese.
Any other question? So
no more questions from
let's thank
from the audience, from the external audience.
I don't have.
They are silent. They are not interested. Okay. Thank you for your patience for an hour and a half.